how come Zer is only regulating 4? They both have the same number of atoms that have to be managed in the cell. And what we're finding is that, in fact, there's a much deeper Zer-Regulon one that just is not well explained by the current data. And I'll be talking more about that in the future, maybe on my next visit here. Okay, so we've seen that there are sensors, and there are now hundreds of these that turn on and off gene expression. Can we use the way they work, and study them in the test tube and try to understand something about how the cell works itself, how much of the metal is free? And so these are the two proteins I showed you before, the Zer protein and the ZMTR protein. But one turns off the import and the other one turns on the export when there's too much zinc. So you hope that they're coordinated in their activities. And what Karen Allen was able to show is that, in fact, Zer turns off the transcription in the test tube in response to increases in zinc concentration. And after it shuts down the zinc upload genes, it then turns on zinc export. So things follow in the natural order. But this narrow range is really fascinating. There's really only a 4-fold concentration change between when you start turning off Zer and turning on ZMTR. And the center of that is around 10 to the minus 16th molar in terms of free zinc. That is an extremely tight binding site. And in fact, if we ask, is that the ambient free zinc concentration in the cell? Well, how do we think about that? The free zinc concentration of one zinc dissolved in the volume element of an E. coli is 1 nanomolar. This is 6 orders of magnitude less than 1 nanomolar. And what that suggests to us in a type of thought experiment is that there's a whole host of chelating agents inside the cell that are competing and binding the zinc and not making it available. But once that pool is exceeded, once that buffer capacity is exceeded, these switches trip on and take control of the transcription of the pumps that will determine the fate of the cell. So if we step back, and I'm not saying that's the ambient free zinc concentration in the cell, but if you agree with me that there's generally extremely low free zinc concentration in the cell, these are highly restricted. I can show you the same type of data for copper, which we've published, and copper is even more tightly regulated. Then there's really no zinc floating around, or copper. So the question is, when you need a copper ion or zinc ion, how do you get it? Another interesting fact is that we have to think about the studies I've just shown you. They're described as thermodynamics. They're really not considering how much time it takes. We assume that the system has reached equilibrium. But a very momentary pulse or an elevation in zinc could really be playing a critical role that other factors are going to be monitoring. And I'm bringing this subtlety out because we're going to talk about this as we go on to the A. And I point out calcium because it's well known that calcium does that. It's an alkali earth metal that doesn't form covalent bonds the way zinc does. But what we want to do is start thinking that there are going to be parallels, or could there be parallels between zinc and calcium. And then I wanted to say, are there pools of